if you take a random variable x with mean mu, subtract it, and standard deviation sigma, divide by it, you should be able to use properties of expected value to verify that this mean of this transformed random variable is 0. How? Yeah, again, use properties of expected value. Dividing by a number, maybe you don't think about this much. Dividing by the numbers is the same as multiplying by the reciprocal of the number. Dividing by sigma is the same as multiplying by 1 over sigma. We can go ahead and write it this way to make that more explicit. So that's a constant multiple of a random variable. One of the linearity properties of expected value said you can factor out that constant multiple like this. So 1 over sigma, being a constant multiple, can come in front of the expected value like that. Here we have the expected value of a difference. Of course, a difference is a sum, right? When you are subtracting 4, you're really adding negative 4. Subtracting mu is the same as adding negative mu. And ultimately, combining more linearity properties, you get this. Mu is a constant, so this expected value is that constant, right? Because mu is a constant. Is mu really a random variable? Well, it depends on how you think about it. It is a constant, it is a fixed number. If you want to think about a fixed number as a constant random variable, you can. You just do a random experiment and you always get that number. This thing is a mu as well, right? Mu and the expected value of x mean the same thing, and they both represent the mean. Mean the same thing, and they both represent the mean. Oh, this is great. Later in the semester, we're going to come across a property that says the mean of the mean is the mean. And I'm serious. I'm completely serious. When we get to that property, that's how you describe it. The mean of the mean is the mean. Here, the mean is the mean. Mu, population parameter, describing the random variable x, is the expected value of x. They're just different names for the same thing. Different symbols for the same thing. That is a mu. Mu minus mu is 0. That's a 0. The answer is 0. I am implicitly assuming in writing all these things that the mean and the standard deviation they do exist. They are finite numbers. I did hint last time that there are some distributions where those do not exist, because you have an infinite sum, for example, that does not converge. That can happen. But I'm implicitly assuming these exist. How about the variance? Variance of x minus mu over sigma. Once again, dividing by sigma is the same as multiplying by 1 over sigma. With the variance, the constant multiple can be factored out as well, as long as you square it. That is true in general, even if the constant multiple is a negative number. You square it, you get a positive number. Sigma can't be negative. I mean, that doesn't really matter here, but just in general, realize when you pull out the constant multiple, even if the constant's negative, you're still squaring it, you're still going to get a positive number in front. I can write this as one fraction if I like. But now what do you do? What's the variance of x minus mu? Is it? Well, okay. Is it the variance of x plus the variance of negative mu? I'm writing it down as if it is here. But what property would I need to know to guarantee that that's true? What's one word? It starts with an I. Independence. In order for this to be true, x and the constant negative mu better be independent random variables. Well, guess what? Any random variable and a constant random variable will be independent. They're unrelated. because the constant's always a constant. It doesn't matter what it is. Doesn't matter what trial of the experiment it is. That other variable will not be affected by it, and vice versa, because it's a constant. So yes, x and negative mu are independent. That allows me to say that. And the variance of a constant is 0. Right? That's the variance of a constant. That's 0. So we get the variance of x divided by sigma squared. But wait a minute. Sigma squared is just another symbol for the variance. This is sigma squared over sigma squared is 1. What we just derived here is that when you get a random variable, any random variable, whose mean mu and standard deviation sigma, and also the variance sigma squared exist, then this new random variable created by computing x minus its mean and dividing by standard deviation will have a mean of 0 and a variance of 1, and also a standard deviation of 1, since the square root of 1 is 1. That's a very standard sounding kind of thing to do. Yeah, this is called standardization. Standardization, when we do this. And it is very common to call this new transformed variable z. Although this can be a little bit misleading with how we're going to use the letter z later on. Most often, x will have what's called a normal distribution later on, not now. Bell-shaped curve, continuous distribution in chapter 4. And z will have what's called a standard normal distribution, still a bell-shaped curve, but centered on 0, the mean of 0, and having a standard deviation of 1, sort of a standard way of describing the spread. In some ways we'll make particular when we get to normal distributions. So z almost always, once we get past chapter 4, will stand for a standard normal random variable. But even if it's not normal, even if it's discrete, for example, people still typically use the letter z here anyway.